Hey everybody, so today we're starting on lesson 3, the ups and downs of thermometers. But before we get to that, we're going to talk about our last lab from lesson 2. So that is the molecules in motion lab that I have pulled up right here. So this is the one I put up online on Wednesday. Okay, so we did this one. So describe what the colors look like, and so talked about this, so we should know. So the question to investigate on this lab, which is important, is the speed of the water molecules different in hot and cold water? And yes, most certainly they are, right? We know that in hot water, molecules move faster than in cold water. And so this doesn't only apply with water, but it applies with all kinds of matter. So the more heat, or if you want to substitute the word heat for energy, so the more energy we give a substance, the particles are more energized, therefore they move faster. Okay, and as we go on with this lab, not only do they move faster, they also move farther apart. Okay, so as we got down here with these animations you guys should have done based on your observations with the animations, filled in increases and decreases. So heating a substance increases the molecular motion, cooling a substance decreases molecular motion. Those are the correct answers. As molecular motion increases, the space between the molecules also increases. Okay, so these particles, they're attracted to each other. They want to be sucked to each other, but they have just enough energy. If they're cold, or if they're not moving very fast, they have just enough energy. They're not going to stick to each other, and they're able to slide past each other. That's a liquid. But if they have a great enough attraction to one another and they don't have enough energy, they will stay vibrating there in place, stuck in place. Okay, and we call that a solid, and we'll get more into that. But anyways, as molecular motion increases, that means it has enough energy where these guys start to spread out more and more. And then we get to, as molecular motion decreases, the spaces between the molecules also decrease, so they become more and more compact. But in these liquids, they're still able to move around past one another. Okay, let me bring that down here just a little bit. Okay, number 6, we talked about drawing if this was hot, right? If this was a hot water, the molecules would be farther apart. They'd be moving faster. If this was cold water over here, the particles would be closer together, and they wouldn't be moving as fast. So then number 7, let's talk about the answer to number 7. So you guys should have turned in this assignment. Okay, it is due tonight at midnight, so let's get that turned in. Using what you know about, all right, so anyways, let's say that you measure a graduated cylinder, you measure 100 milliliters of water, and you heat the water to 100 degrees Celsius, and notice that the volume has increased to 104 milliliters. So what happened? So you started right here, you have exactly 100 milliliters, you're at room temperature, and then you heat it up to 100 degrees Celsius, which is the boiling point of water. Okay, you heat it up a lot, and it's actually increased 4 milliliters. So what's going on? Is there more water entering this graduated cylinder? Is it just coming out of thin air? No, that's not the case. Okay, so just like what we talked about, as you increase the heat to something, you increase the temperature. These particles, they start moving around a lot more, and they start spreading out, and so it gives us this look that there's more water, but in all actuality, the water itself is all expanding. Now, the H2O particles are not expanding, but they're just moving farther away. So the water itself in the graduated cylinder is expanding. Okay. And so that is pretty much the answer right there to number 7. Okay. And so before we get into this ups and downs of Thermometers Lab, I started out class today with, I asked a question to everybody, and I said, can metal float on water? And for the most part, everybody said, yeah. If I put a block of iron in water, it's going to float, or it's going to sink, no problem. And they're correct most of the time. Okay, and I just had my stuff here, and I don't have it with me. Oh, here it is right in front of my face. I did have it. Okay, so anyways, I gave everybody a cup of water here. We filled up this cup of water. But then I gave everybody going the wrong way, giving everybody a paper clip, and we bent it in this fashion. Okay, and what I'm going to do is I'm going to put this bottom part on the water, and I'm going to try to do it really slow so that it will sit on top of the water here. All right, so I don't know if you guys can see that, but a paperclip is floating on water. Nuts, right? It's actually not floating on water. Okay? The moment that I push this guy through the surface, it sinks right to the bottom. So it's not floating on water, it's actually sitting on the surface. So what's going on? Why is it sitting on the surface of the water? Well, there's something that we like to call surface tension, okay? And so we just got done talking about how water particles, or all particles, are attracted to each other. So the particles at the surface are being pulled down by the rest of the attractions underneath of them, and they have nothing above them because they're on the surface. And so essentially they're being pulled down. And so I drew a little thing here to show you guys. So if these are the surface molecules up here, they're being pulled down by these other water molecules down here, and they're just being pulled downwards, being stretched tight, right? And then the second that we broke one of these attractions right here, right, then it just sinks to the bottom, because these guys then are just being pulled up, down, left, right, where the guys on the surface are just being pulled downwards, okay? And I also attached a link of surface tension, another guy that has some better animations than I do, that explains this a little better, and I encourage you to really watch that, okay? So there's our surface tension. That's effectively what's going on, is we're putting that paper clip on top of here, and it's sitting on the surface water molecules, okay? So it's not floating, because once it breaks through, it just sinks right down, okay? And so I've been talking about attraction, so these guys are attracted to each other, but why, okay? And so I also drew up this. And so our H2O molecule, right, looks like this guy right here. There's one oxygen, two hydrogens. The oxygen is actually partially negative, while my hydrogens are partially positive. And so we know that opposites attract, right? If we have a magnet, only the opposite sides of magnets, so a negative side will be attracted to the positive side. But if I put a positive and a positive together, they repel each other. If I put a negative and a negative together, they repel each other. So an H2O particle is actually polarized, kind of like a bar magnet, okay? Which we're going to talk about some other substances that don't have as strong as pole as water molecules, and they're not as polar, or they're non-polar at all, meaning they don't hardly have any attractions to each other, meaning like alcohol. Okay, so if we have alcohol, like rubbing alcohol, if you ever rubbing alcohol on the desk, just like a thin film, versus rubbing a thin film of water on the surface, the rubbing alcohol will actually evaporate much faster than the water will, because they're not attracted to each other near as much as water is. And so they don't really care to hold on to each other, and they'll just fly off into the atmosphere, no problem, because there's no attraction holding them to each other, or there's hardly any attraction. Where water will stick together, it takes more for them to evaporate, because they're attracted to each other. They want to hold and stick to each other. All right, so let's go on with our lab here. So I have my lab 3 right here for you guys, and on my screen. All right, so let's start off here. So we're looking closely at this thermometer. So here's our question of the day. What makes the liquid in the thermometer goes up and down? So in this thermometer that we're looking at, it's actually alcohol. Okay, so I have a scientific thermometer right here. You guys can see the red right there. Okay, so it says look closely at the thermometer. The liquid inside is probably a type of alcohol that has been dyed red. Yes, that's correct. Read the temperature in Celsius at eye level. So anytime that I want to read a thermometer, I'm not looking at the red line that's right here. I'm not going to have my eye level up here, and I'm not going to have it up here either. I want to be looking at it eye level so I can get a nice accurate reading. So as I have this eye level, I see that it's 23 degrees Celsius. That is 22 degrees Celsius considered room temperature, 23 degrees Celsius, it's room temperature. Okay, and then what it tells you to do is put your finger on the red bulb, like I'm doing right here at the bottom. So this is where the temperature is being gauged at. And if I hold it here with my finger and my thumb, I can slowly start to watch it climb. There we go. It's at 24. It was at 23. Oh, will it climb any more for us? Just a little bit, maybe. Anywho, we're not going to send here, but it works, promise. I promise. Okay? So the next part, which we can do, is I have a this glass of water here, which is room temperature. And then I have another one right here that I just got done boiling. So it should be close to boiling or warm. Okay, so this is my hot water. This is my cold water. Okay, and so we all know what thermometers do. We use them every single day. But if I keep this guy here in the water just for a few minutes here, it should be able to give me a room temperature reading, which is going to be pretty close to what it was already, right? It's been sitting out in the air. So if my air is already 23 degrees Celsius, then my water is most likely going to be about 23 degrees Celsius. So I get down here, wait for a second, make sure it's not moving anymore. And it is. It's 23 degrees Celsius. Okay? So that's what you would write down on your second one. Sorry. So I started out with the room temperature. Or the cold one. So let's go over to the hot water, which is right here. And as I watch it, can you guys see it climb? You can. Yeah, so you can barely see the red alcohol skyrocketing. It's about 40 right now. It's climbing just above 40. Okay. Let's see, and I've been letting it sit around since I started this video, so it's probably cooled off quite a bit. And it's actually sitting at about 44 degrees Celsius, okay? 44 degrees Celsius. So that's warm water, okay? Not super hot, but warm water. But that's enough to give us a feel for what a thermometer does. And so now we're going to talk about how does a thermometer actually work? How does it actually gauge the temperature of a substance? So let's kick into this. So number 3 says, based on what you know about the molecules move in hot liquids, explain why the liquid in the thermometer goes up when heated. Well, there's a liquid in here. It's alcohol. Okay. And we know that liquids, or any matter for that example, if you warm up that matter, the particles will begin to move faster. As the particles move faster, then their space increases between all of the individual particles in this liquid. Okay, so as the spaces increase between the particles, then the liquid as a whole expands. Okay, and then number 2 is just the exact opposite of that. Based on what you know about molecules, the way molecules move in cold liquids, explain why the liquid in thermometer goes down. Well, we take away energy, the particles begin to slow down, the attractive forces begin to take over because they're slowing down, they're getting closer together, and they're like magnets, right? Because they are attracted to each other somewhat. Like I said, alcohol doesn't have as great as of attraction between the other particles as water particles do to each other. But still, there is a little bit of attraction. That's why we're able to see it in liquid form. If there was no attraction, then they would be a gas and they just fly away from each other because they have no reason to stick together in a liquid form or a solid form. Okay, so it cools down. Spaces get closer together, or they become smaller, I should say, and the attractive forces begin to pull them closer and closer. Okay, and then number 3, why do you think that the tube that contains the red liquid is so thin? Well, number 1, it takes less energy to heat the less substance you have, the less energy you need to heat it up. And the less of that sample you have, it will cool off faster, right? And then on top of that, why is it so thin? Well, we want to be able to detect small amounts of temperature changes. Okay? Yes. What's up? Let me try to pause this real fast. And you can just put it there. Thank you. You're all right. All right. Mrs. Keene dropping in on my class. Okay. So anyways, where are we at? Number 3. Why do you think the tube contains red? Okay. Now I lost my train of thought. Okay, so the less amount of liquid. So if we have a smaller amount, we can detect more subtle temperature changes. And that's why. Whether if we had a larger one, then it would take more energy to heat up more alcohol, and we wouldn't be able to detect those subtle temperature changes. Okay, and then number 4, it doesn't have a whole lot to do with our lab, really. It's just, this is already small enough. It can be kind of tough for some people to read these. So if my tube, so we see, you guys see how thin this red liquid is. What if the tube was as thin as the red liquid itself? Well, then we wouldn't be able to read anything, right? You would literally need a microscope or a magnifying glass to read what's written on there, right? So there's number one. Number two is this thicker outer glass tube acts as a structural support, so it's not as easy to break either. So last year, I think like 2 or 3 of these thermometers of mine, we did this lab, and 2 or 3 of them broke. Okay, so they're still kind of easy to break, but making them a little thicker allows them to stand up to some more things like that. Okay, number 5. So then we have an animation, right? So it's a very similar to animation that we've already watched the last lab, and it is right here. Okay, so the heating and cooling of a liquid. Let's see what this looks like here. Drag it over like this. And I want it to come down a little bit. And I'm going to press play. All right, so this is the one we watched the other day. So this one has to do with the graduated cylinder, right? I don't want that one right now. I want this one. It's the same one. I have too many pull-ups. All right, here we go. Heating and cooling of a thermometer. All right, so essentially it's the same thing, except we have a thermometer in this one. So room temperature, we see the alcohol here. We see the alcohol molecules here, and they're bouncing around at room temperature. They have a little bit of space in between them. They're mildly energetic, right? Let's cool it down a little bit. The thermometer begins to fall down. That's because the spaces between the particles are becoming smaller. The particles are moving slower. The attractions between them are pulling them closer together. Room temperature, we're heating it up. The attraction is becoming a little weaker because they're more energetic, and the space is becoming greater. The hotter it is, again, these particles then get really energetic. The spaces between them becomes a lot more because they're moving faster. Therefore, the liquid as a whole begins to rise and go straight upwards. Okay? So, let's go ahead and go back to our lab here. All right, so based on this, what you know, I'm going to start down here. Try to show the difference in distance between the molecules when the liquid is hot and cold. Use the motion lines to represent their movement. So again, it's just like what we did the last couple days. Is in the hot, the particles would be farther apart. They'd be moving faster. Here in the cold, they would be closer together and they would not be moving as fast. Okay, and so today in class, we got to this part with one of my classes, and then the rest of them we did not. So I said that we would start off with this on Tuesday, so you guys don't have to turn this in until Tuesday. But I'll go ahead, and if you guys want to turn it in today, or if you finish it up, just have it in by Tuesday by midnight. But number 6 says, imagine that you have 2 thermometers that are identical in every way, except for one thermometer has mercury, and the other one has alcohol. Okay. Each thermometer is placed in hot water that is 100 degrees Celsius. So that's the boiling point of water. The levels of alcohol and mercury are shown in the picture. So we see right here that this alcohol thermometer, we see that it shows 100 degrees Celsius, but the level of alcohol is way up here, where mercury over here, the level of mercury is right here, and it still shows 100 degrees Celsius. So what's going on? It says, why do you think liquids in the thermometers are at different levels, even though they're in water that are the same temperature? Okay, so what can account for this? Alcohol, here's our hint here, is alcohol and mercury are both liquids, but they are made of different atoms and molecules. Use what you know about motion. Okay, so motion. What do you know about motion? What do you know about attractions of particles in a liquid? This should be directly involved. I should be hearing both of these things. You talk about both of these things when you answer and turn this in. So what do you know about the motion and attractions of the particles in a liquid have for one another to explain why the levels of alcohol and mercury in the thermometer are different? All right. So if you guys have any more questions for me, let me know. Please email me, but this will be due Thursday by midnight. Okay, next class period we'll probably be doing some notes. I'll send out a PowerPoint and things like that, but please get this uploaded to Teams whenever you can. Thanks.